Hi there, welcome to this lecture series on matrix algebra. This is lecture 27, part 1. In this lecture, we'll talk about Markov chains. First, we will take an example where a Markov chain would occur. This example is an example of a random queue. Assuming now every minute a snapshot is taken at a supermarket counter, checking how many customers are in the line. And let's say the number of customers in the line are either 0 or 1 or 2. So we have the set of possible numbers of customers there, and let's say xk would be one of them. So it's in this set that has a collection of these three numbers. And these are like random number of customers at time k that we assign to this variable capital Xk. So we wish to understand the following question. That is, assuming now that the counter initially is empty, so x0 is 0, there's no one there, then what is the probability that x at time k, that it can be 0, or be 1 or be 2. So the probability of all different situations. And then we want to understand it for all future times k from 1, 2, 3, and so on. So here we will define a so-called Markov chain. It is described in terms of something we call transition probabilities. Let's have a variable a with index I and j. What does that mean is it measures the probability of jumping from state j to state I. Okay, so it's from the right one jump to the left index, the state. So in other words, this would also be the measurement of the probability that xk plus 1 equal to I, subject to that at xk, at the previous one, it's j. So at xk, it's j, and then the next step, it becomes I, and I measure the probability of that happening, and this probability is denoted by aij. So in our example, we have three possible states, right? 0, 1, and 2, and then we can form this matrix A, which collects all the transition probabilities in it in the following way. I'll just put A00, A01, A02 in the first row, and then A10, 11, 12 in the second row, and the third row will be 20, 21, and 22. So what does that mean? So A00 will be the probability and jumping from state 0 to 0. And then A10 will be jumping from 0 to 1. And then A02 is the probability of jumping from 0 to 2. And so on and so forth. Now let's say we did some analysis and then we figured out the probability of this process, and that we fill in the numbers and we have this matrix. So what does that mean is that the probability is half if you are initially 0 and then at k plus 1 you are still 0. And then the probability is also half if you are initially 0 at k0 and then at k plus 1 you become 1. And then the probability is 0 if you jump from 0 customer to 2 customer in 1 steps. Okay, and then this will be for when you have 1 customer at k, and then the probability at k plus 1 of having 0 customer or 1 customer or 2 customer, they are equal. They're all 1/3. Okay, and then the last one will be if at xk you have 2 customers, the 2 here, and then that's the probability that at k plus 1 you have 0 or 1 or 2 customers. So at 0, the probability is 0 to have 0 customers, and for the other two cases, the probability is half. So we note that the columns of A, if you add them up, they all have the same sum, that is 1. So the first column, let's see here, these three, you add up, you see it's 1. And then the second column, you add up 3 1/3 is 1. And the third column is also 1. So it should be 1 because they add up these three numbers in the column describes the probability of when you initially are 0, and then all the other possible states you could jump into. This sums up all the probability, and in the end it must be 1. So we want to use matrix and vector to analyze this process. So let's define a vector of probabilities. We define a vector vk, which is, it has 3 elements. The first is the probability that xk is 0. And then the second is when the probability when xk is 1. And then the third is one probability when xk is 2. Okay, so here the k is the time step k. And then this model that we just described here would give us this inductive relation, that is vk, the probability you are at step k depends on the probability you have at k minus 1 multiplied by this coefficient matrix. So if we write out each term in this equation here, vk would be the probability at k for xk to be 0, 1, or 2. And this part here, that's the matrix of the transition probability. And then times the vector, which is the probability of x at k minus 1, the previous step, be taking the value 0, 1, and 2. So we see that in the end, we need to compute to the power a to the power k. So we know that v1 is a times v0, and v2 is a times v1, and then vk is a times vk minus 1. And we have done this before. That is a simple induction step will show us that vk is a to the power k times v0. And here we will be using the A matrix, the transition probability matrix. And then in order to find an expression for a to the power k, we need to compute the eigenvalues and the eigenvectors. So this we know how to do. And let's say we carry out the calculation for the eigenvalues of A, and we find 3 eigenvalues. Lambda 1 is 1, and lambda 2 is half, and lambda 3 is negative 1/6. And then we carry out again the calculation for the corresponding eigenvectors, and then we find 3 of them. W1 correspond to lambda 1, W2 correspond to lambda 2, and W3 for lambda 3. Now we can set the matrix that we usually call P by collecting the eigenvectors as its columns and then form a square matrix. If I collect the numbers and I see that, I get this one. And then this is an invertible matrix, and we can find its inverse. And let's say we carry out the calculation, and then we found that this is the inverse of P. And then we know that P inverse times A times P will give us a diagonal matrix. So we can diagonalize the A in this way. And then on the diagonal, we will have the corresponding eigenvalues. So once the P and the D are obtained, then we can write out a formula for all the powers of k. So A to the power k would be P times D to the power k times P inverse. And we have the expression for each term, so we can put them up. That's P, that's D to the power K, where the power is only on the diagonal elements, and this is P inverse. Okay, so we have shown that now Vk, the probability at step K for the x to take value 0, 1, and 2 can be computed by taking V0, the initial condition, and then we multiply this with a to the power k times V0. That will give us Vk. Now let's try to answer the question. The question says, initially, there's no one at the counter, which means initially x0 equals 0. That means the V0 would be 1, 0, 0, right? Because the first position is 0 customer, and this is 1 customer, and this is 2 customer. And I have no customer, so it's 100% probability 1. This is in the first position. So I have the initial vector. And then we can just use the formula. Vk would be, that's the P, and that will be the D to the power K, and that's P inverse, and this is V0. Okay, so giving us a K, and we can carry out this product and find out what is Vk. So what is interesting here would be the so-called large time behavior. That is, when K is large, when we let this Markov chain, the Markov chain process go on for a long time, what would be the long time behavior? So then the term that involves K is the D to the power K. So here when K is very large, what happens? Well, 1 doesn't change, and 1/2, each time you raise up the power K, you reduce the magnitude of this number by half. So it will converge to 0. And this one also, each time you increase the K, you multiply the amplitude of this number by 1/6. So it converges to 0. So when K is very large, these two numbers are almost 0. So we can approximate DK by very well by this matrix with 1 on the top diagonal and 0, 0 here on the other two diagonal. So this would allow us to compute the power a to the power k when k is very large. What does it approach? So it's this computation here, and we can replace the dk by our approximation, and we get an approximation to this product. So that's P, that's a d to the k approximation, and this is P inverse. So we have a 3 matrices multiplication. So we can carry out this, but with that first, then you get this matrix here, and then multiply by that one, and you carry out that multiplication, and you see you get this. Let's take a look at this matrix here. We notice that if we look at each column, column 1, column 2, column 3, and we see that they are the same. Curious, huh? So as a consequence of that observation, we actually can see that the limit probability as k goes to infinity does not depend on the initial condition. So we can check it easily. Let's take the initial condition to be x0 equals 0. Then I have v0 is 1, 0, 0. And then I can compute ak times v0, where approximately when k is large, ak is just that, and that will give me the first column, which is we wrote down here. And then let's check the other situation where an x at 0 is 1. That means v0 now takes 1 on the second position. That's when the number of customer is 1. And then we compute ak of v, and which means this matrix times that, and then you would just have the second column. And the third case, when x0 equals to 2, and then v0 will have 1 in the third entry, you carry out the same similar calculation, and then you will pick up the third column, which is the same. So all three are the same. We also remark that the vector here that we obtained is actually an eigenvector of A corresponding to the eigenvalue lambda equals 1. Now let's give a definition to this special type of matrices. We call it Markov matrices. So a Markov matrix is a square matrix n by n, and let's say A, and the element is Aij. So this matrix will satisfy the following. Each entry Aij lies between 0 and 1. It takes a value between 0 and 1. And then second, the sum of elements of each column is the same, and they are all 1. So A1j plus A2j to all the way to Anj equals 1 for all j's from 1 to 3 to n. So here, what is the Aij? That is the probability of jumping from state j to state I. So we repeat that. So as a consequence of that definition, we immediately have some result on the eigenvalues. So here's the theorem. Let A be a Markov matrix. Then lambda equal 1 is an eigenvalue of A. Second, every eigenvalue of A satisfies that the absolute value of the eigenvalue is less than 1. Now let's give a proof for probability 1. Lambda equals 1 is an eigenvalue of A. So we know by assumption the elements of each column of A adds up to 1. And therefore, if we look at A transpose, then the elements on each row of A transpose adds up to 1. Now we consider a vector E, which has 1 on all the entrants. And then we claim that A transpose times E is E. Now let's check if this claim holds. A transpose times E equals E. So let's write out A transpose and multiply by E, which is a vector with all 1. Do I get a vector with all 1s in the end? Well, we can take a look at one entry. Let's pick entry number 2. You can pick any entry. And how is this number computed? Well, it is taken this row here, and then in the product, this column. Since these are all 1s, this number is computed by adding up all of these. And then we know they all add up to be 1, so therefore you get all 1s. Okay, so this relationship, this identity is true. So we have proved A transpose times E equals E. What does it mean? Well, this looks like an expression for an eigenvector with 1 in front. So lambda equals 1 is an eigenvalue of A transpose of A matrix, and the eigenvector is E. Now we can use the property that A and A transpose would have the same eigenvalues, because if you write out the characteristic polynomial, the determinant of AT minus lambda I is the same as the determinant of A minus lambda I. Okay. And therefore lambda equals 1 will also be an eigenvalue of A, not only A transpose, but also A, because the same. But we have to be careful. So for the A transpose, we would have an eigenvector here. But for the A, we don't know the eigenvector. It's possibly a different eigenvector. Okay, so that is some property of this Markov matrix. And we'll take a break here. And on the second half, we will take some more examples. Okay, so I hope you enjoyed this one. I'll see you soon.